Welcome to the Signal Tap Logic Analyzer online training. My name is Steve. While watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. By the end of this training, you will understand the many advantages of using the Signal Tap Embedded Logic Analyzer for debugging your FPGA designs. You'll see just how easy it is to add the logic analyzer to your designs and configure it for your unique debugging needs. You'll be able to take the signal data captured by the logic analyzer, analyze it, and use it for further debugging, for documentation purposes, or to get a better understanding of how your design works. Finally, you'll learn about some of the additional features of the ELA that go beyond the standard system debugging flow, but help make the task of verifying and debugging designs even easier. Here is the agenda for this 4-part training. In Part 1, you got an introduction to the Signal Tap Embedded Logic Analyzer, including a quick start guide for implementing and using the logic analyzer. Here in Part 2, we'll expand on what you learned in Part 1 and look at many of the configuration options available for the logic analyzer, including the many options for defining basic trigger conditions. Subsequent parts of this training, available on the Intel FPGA training website and linked at the end of this training, provide more detail on the tool, including more information about compiling and recompiling a design that includes the logic analyzer and programming a device with that design. You'll also learn about advanced triggering options that you can use to capture those hard-to-catch signal events. Finally, Part 4 covers some more advanced features available in the tool to help simplify the debugging process. The whole idea behind the logic analyzer is to be able to capture signal states around when defined hardware events occur, referred to as triggers. Once nodes have been added to the node list, you have many different options for creating trigger conditions. On the right side of the node list are one or more trigger condition columns. Each column represents a single trigger condition. You can have up to 10 different conditions for a single signal tap instance. The number of trigger condition columns is specified in the logic analyzer settings, which we'll look at later. Each condition can be one of several different types, set at the top of the column. Basic triggers are the simplest types of triggers to create using the trigger condition columns. A basic trigger is a simple Boolean comparison between all the trigger-enabled signals in a trigger condition column. For each signal or group of signals in the node list, specify the state or transition direction when the trigger should occur by right-clicking a cell in the column and selecting an option. We'll look at these options shortly. A basic AND trigger type is the default. Once the values are set for a column, the trigger will occur for a basic AND trigger when all the trigger-enabled signals are at the setting specified on the rising edge of the sampling clock. Only trigger-enabled signals are monitored for values set in the trigger condition columns. To set these values, right-click the value cell for an individual signal or a group. The right-click menu shown here will appear. The options available in the menu vary depending on the type of trigger condition and whether the value is being set for an individual signal or for a group. For basic triggering on individual signals, simply select the high or low signal level or an edge transition. Select Don't Care if the status of the signal is not required for the trigger condition. For setting a value for a bus or group, there are several options. You can either type a value directly in the node list or right-click and select Insert Value. In the Insert Value dialog box, enter a value for the signals in any desired radix, including binary, hexadecimal, or even IEEE 754 floating point. Another way to quickly create the values for a group is with a mnemonic table, described in a moment. With a mnemonic table defined, basic triggers can be quickly set using labels from the table instead of manually setting individual signal values. To make it easier to set group values for triggers and recognize the meaning of specific bit patterns in group capture data, you can create mnemonic tables. A mnemonic table is simply a table where specific bit patterns are associated with recognizable names or labels. Mnemonic tables can be used in both the Setup and Data tabs of the Signal Tab file window. On the Setup tab in the node list, an entry from a table can be used to define a trigger, as seen on the previous slides. As seen in the Data tab in Part 1 of the training, a mnemonic table can clearly display the meaning of a bit pattern in the captured data without having to decode the bits. Tables can be created manually using the Mnemonic Table Setup option. Tables can be created, edited, or imported from other .stp files. In the example shown here, the table maps names to bit patterns that represent signals that drive a 7-segment display. Once a table is set up, it must be applied to a bus or group of the appropriate bit width. To do this requires a two-step process. First, the table needs to be specified as the display format for the group. Right-click the group name in the node list and select the table from the Bus Display Format submenu, found near the very bottom of the right-click menu. It's a little easy to miss. While here, you can adjust other aspects of how the group is displayed in the node list, such as the endianness, whether the bus's most significant bit is listed first or last. Once the bus display format is set to the mnemonic table, right-click the value cell for a group in a trigger condition column and select an entry from the table. The mnemonic selected will appear in the value cell for the selected group. As mentioned, for each of the trigger condition columns, you have a choice of different trigger types. The 4 types are shown here. We've already looked at basic AND triggers. For a basic OR trigger, if any one of the signals match the specified level or transition, the trigger condition is met. Bits in signal groups are essentially OR reduced, unless the condition is a numerical value. A comparison trigger expands the features of a basic OR trigger by comparing the bits of a group to an integer value. We'll examine these trigger types in more detail in a moment. Finally, you can select an advanced trigger. This lets you create more complicated Boolean expressions to check the trigger-enabled signals against. We'll look at advanced triggering later. One extra feature of the trigger condition columns is the ability to enable or disable any trigger condition without recompiling. After creating multiple trigger conditions, you may decide later in the debugging process that you do not want the logic analyzer to monitor for that condition, perhaps because the condition isn't occurring in your design. Simply turn off the checkbox at the top of any trigger condition column to disable that condition. This can be done without recompiling the logic analyzer. The basic OR trigger type has some additional functionality. To understand what you can do, it's important to understand the concept of a nested signal group. A nested group is simply a collection of signals within a group that are combined into their own group. You can use nested groups to organize the signals within a group or to create more complicated trigger conditions. To create a nested group, simply select signals within a group, right-click, and select Group. When this is done, the original group is referred to as the parent, and nested groups are referred to as the child groups of the parent. Note that for a basic AND trigger, signal monitoring with nested groups behaves the same as if there were no nested groups at all. All signals must match the selected level or type of edge transition for the trigger to occur. This behavior changes, however, with a basic OR trigger. Without nested groups, a basic OR trigger is what you'd expect. Any one of the signal values must be true for the trigger to occur instead of all of them, as is the case with a basic AND trigger. However, once signals are grouped together, you can create advanced trigger conditions that perform advanced Boolean checks between the signals within groups and between the groups themselves. From the right-click value menu for a parent or child group, select an evaluation method. The signals within the group will be evaluated against each other using the selected method. For nested groups, these checks are performed in a bottom-up fashion. The lowest level group gets evaluated first, returning a logic 1 or 0 to the parent group. This value is then used to evaluate against higher level groups or signals using the selected evaluation method for the higher level group. If you want to ignore the evaluation of nodes within a nested group, you can set the evaluation method to either true or false. The nested group evaluation will always return 1 or 0 respectively, which will then be used for the higher level group evaluation. In the example shown here, on each rising edge of the sampling clock, first, the values selected for the 4 individual signals within the child group are XORed together. Since XOR is selected, if only one of these signals matches the level or signal transition edge specified, the child group returns a 1 to the parent. The resulting 1 or 0 from the child group is then ORed with the values of the 3 signals in the parent group. The final result of this OR operation determines whether the trigger condition has occurred or not. The final basic trigger type is a comparison trigger. A comparison trigger is an extension of the basic OR trigger. With a comparison trigger, the numerical value of a group is checked against either a single value or checked to see if it is within a range of values. To use this trigger type, right-click the value cell in a trigger condition column for a group and select Compare. In the Compare dialog box, select either a single value comparison or an interval check. For a single value comparison, select the type of comparison and the value to compare against. Evaluation of the group returns logic 1 when the comparison is true. For an interval check, specify the upper and lower bound values and whether those bounding values should be included in the range or not. Evaluation of the group returns logic 1 when the value is within the specified bounded range. Once you've set up a comparison trigger, you can edit the comparison directly in the trigger condition column without reopening the Compare dialog box. You can also freely switch between the comparison and basic OR trigger types during runtime without having to recompile the logic analyzer. Now that you know the basics of creating trigger conditions, let's take a look at the options available for configuring the tool for a specific debugging situation. As mentioned in Part 1, all basic configuration of the logic analyzer is performed using the Signal Configuration section of the SignalTap file window. The Signal Configuration pane is where you specify a sampling clock, set the characteristics of the selected instance's memory buffer, and configure the use of triggers. You can configure these options either before or after you've tapped signals and set up trigger conditions. If you have used external test equipment before, such as oscilloscopes or logic analyzers, some of the settings discussed here might be familiar. At the top of the Signal Configuration pane of the SignalTap file window, select the sampling clock to use for the selected instance of the logic analyzer. As mentioned in Part 1 of the training, this is required for using the logic analyzer. The sampling clock is similar to the triggering clock generated by a bench logic analyzer. For SignalTap, however, you need to select a signal in the design to act as the clock. Typically, this will be the clock that drives the tapped signals. However, this is not a requirement. Any signal in the design can be used as the sampling clock. You select the clock signal using the node finder in the same manner used to tap signals for analysis. Data is sampled on every rising edge of the sampling clock, so a faster clock will provide better sampling resolution. If you do not specify a sampling clock by the time you save the .stp file, a default signal named auto-stp external CLK will be selected as the sampling clock. Since a clock is required and no clock was specified, this signal must be connected to an external clock pin on the device for use by the ELA. This signal will appear in the All Pins list of the pin planner. The logic analyzer will not compile successfully until a sampling clock is specified. The ELA provides several options for how the memory buffer for a given instance is configured. The sample depth setting determines how many samples should be captured for each tapped signal. As mentioned earlier, this value can be set to a maximum of 128K samples. However, setting a high value for the sample depth can quickly use up available memory resources. Check the resource usage estimator in the Instance Manager, if supported in your version of the Intel Cortex Prime software, to make sure this doesn't happen. The RAM type setting lets you specify which type of memory block resource you'd like to use to implement the buffer. By specifying a RAM type, you can reserve the selected type of memory for use by the logic analyzer, preventing the tool from using other memory that may be needed for the main design. This setting is only available for devices that have more than one type of memory block available. If your device does not include multiple memory block types, or you don't need to reserve a specific type, set this to auto. The next setting is used to select how the buffer will be implemented. Signal tap buffers can either be non-segmented, similar to a FIFO, or segmented into a selected number of evenly sized segments. A non-segmented buffer is the default and is selected by turning off the checkbox. So what is the difference between these two buffer types? A non-segmented buffer is more familiar and what is typically used on external test equipment. The buffer behaves like a FIFO. Newly sampled data is constantly brought into the buffer and shifted through. The oldest samples are removed at the end of the buffer. When all defined trigger conditions occur, the logic analyzer keeps whatever samples are currently in the buffer, but continues to capture and store a predetermined amount of post-trigger data samples, typically filling up the rest of the buffer before stopping the analysis. Captured data from before the trigger is called pre-trigger data, while data captured after the trigger is called post-trigger data. The location of the trigger within the data is set by the user. Setting a pre-trigger position stores more pre-trigger data that was already in the buffer before the trigger occurred, and less post-trigger data. The center trigger position stores an equal amount of pre- and post-trigger data, while a post-trigger position stores more data from after the trigger occurred than before. Here is what data captured with a pre-trigger position looks like in the Data tab of the Signal Tap file window. The majority of the captured data is from before the trigger event, indicated by the dashed line at sample 0. In this design, the trigger occurs when a counter equals 0. This screenshot also shows you one way you can view samples of captured group data, as a bar graph, with the height of each bar indicating the sampled value of the group. The other buffer type available is a segmented buffer. The full sample depth is divided into a selected number of evenly sized segments. For example, a buffer with a 4K sample depth can be divided into 4 individual 1K size segments. Each segment of the segmented buffer behaves like a smaller non-segmented buffer. When the trigger occurs, only a single segment is filled instead of the entire buffer. Subsequent segments are filled when the trigger condition occurs again. If there are multiple trigger conditions, subsequent buffer segments are filled when the final trigger condition repeats. In this way, the segmented buffer becomes very useful for capturing data about recurring trigger events, allowing you to use allocated buffer space more efficiently by only capturing relevant data samples around the recurring event. Here's what captured data with a segmented buffer looks like. This buffer is divided up into 4 segments, so the trigger condition must occur 4 times to completely fill up the buffer. In this design, each segment is triggered when a counter's value is 0. Each buffer is 16 samples deep, and the pre-trigger position is selected. The pipeline factor setting lets you insert up to 5 pipeline stages into the logic analyzer design to potentially increase its maximum performance, which is calculated when performing timing analysis. Adding pipeline registers to a design is a good method for increasing Fmax. However, There is no guarantee that increasing this value will improve performance unless the registers get placed on critical timing paths, which is not guaranteed with this option. Note that even though this option is available, the logic analyzer is not currently optimized and implemented using the hyperregisters found in HyperFlex architecture devices. In these devices, registers are available almost everywhere throughout the device, including directly in the routing fabric. The Intel Cortex Prime software can enable the use of these special registers and precisely place them to better balance out path delays and increase performance. The compiler does this near the end of the compilation process after the main logic of the ELA is placed. To learn more about optimizing a design in a device with the HyperFlex architecture, search for HyperFlex in the Intel FPGA training course catalog. The next group of settings are used to set up storage qualification. Storage qualification lets you choose which captured samples should be stored in the buffer, based on several customizable conditions. Storage qualification only works with non-segmented buffers. Normally, captured data in a non-segmented buffer looks like the picture shown here. When the trigger occurs, pre- and post-trigger data samples are all stored in the buffer until the buffer is full, with no regard to whether the sample contains useful information for debugging or not. For example, there could be a series of samples where an important signal is idle, wasting buffer space that could be filled with samples where the important signal actually toggles. With storage qualification, the logic analyzer is configured to not store every single sample around the trigger. By skipping the capture of some samples based on customizable conditions, additional samples that occur later in time that would normally not fit in the buffer can now be stored and analyzed. Locations of data discontinuities caused by skipping samples are marked, if desired, in the capture data. Thus, even with a small buffer depth, only desired samples are captured, providing the most efficient use of limited space. Note that with storage qualification enabled, it's possible that the buffer may never completely fill. Since storage qualification is like putting a write enable signal on the buffer, that signal may not be active long enough to fill the buffer. The logic analyzer automatically stops running only when the buffer is full, but as noted earlier, you can manually stop the logic analyzer at any time. Even if the buffer is not full due to storage qualification, you can still view the samples that were captured. There are 6 types of storage qualification that can be performed. Continuous is the default setting and is equivalent to not performing any storage qualification. All samples around the trigger are stored. The input port qualification type lets you select a signal, either internal or on an input pin, that will be basically used as a buffer write enable signal. If the selected signal is high on the rising edge of the sampling clock, samples are stored in the buffer. Transitional qualification causes samples to be stored when selected signals in the node list transition from high to low or from low to high. When this type is selected, additional columns with checkboxes appear in the node list to select which signal or signals to watch. Conditional and start-stop types are similar. For both types, Boolean conditions are defined, using the same basic trigger types and conditions described earlier, to define when samples should be stored. For conditional, only samples where the Boolean condition evaluates to true are stored. For start-stop, when the start condition is true, data is stored continuously until the stop condition is true. For both these types, additional columns are added to the node list to select which signals should be used to define the conditions and to define the conditions themselves. Finally, the state-based type provides complete control over when and how samples are stored when using the state-based triggering flow, which we'll look at later. The other storage qualifier settings let you select the input port for the input port qualification type, mark in the waveform viewer where data discontinuities occur due to storage qualification, and disable storage qualification on the fly during runtime. With this setting, you can instantly turn off qualification during analysis without having to recompile the logic analyzer. Changing the storage qualification type, however, will always require a recompile. With multiple trigger conditions available, you have complete control over the order in which the logic analyzer looks at each condition using the trigger flow control setting. Two options are available: sequential and state-based. With the sequential trigger flow, the trigger condition columns are evaluated sequentially from condition 1 up to the number of conditions selected before the logic analyzer triggers and the sample data is stored in the buffer. If a trigger in is enabled, discussed later, the logic analyzer looks for it to occur first before any of the trigger conditions. The other flow control option is a state-based trigger. A state-based trigger flow is controlled by user-defined trigger evaluation states that may include any combination of trigger condition evaluation, custom flag and counter control, and transitions between states. The states also control how a circular or segmented buffer will get filled. We'll look at the state-based flow in the next part of the training. Let's look at the sequential flow graphically to get a better understanding of how it works. On the left is the flow for a non-segmented buffer, and on the right is the flow with a segmented buffer with M segments, both with N trigger conditions configured. The sequential flow starts the same for both types of buffers. If there is a trigger in, it is evaluated first. Next, trigger condition 1 is evaluated, if it is enabled. Remember, trigger conditions in the sequential flow can be disabled using the checkboxes at the top of each trigger condition column. With both types of buffers, the logic analyzer has to check and see whether more trigger condition columns are enabled. This check must happen after each trigger condition occurs to determine whether to stop and fill the buffer or continue checking conditions. If there are no more enabled conditions and the last trigger condition in the sequence occurred, the logic analyzer stops and the buffer is filled based on the storage qualification settings. If there are more trigger conditions, the ELA will watch for trigger conditions in sequential order, skipping any disabled conditions. With a segmented buffer, sequential enabled trigger conditions are evaluated until the last trigger condition N occurs. At this point, the first segment in the buffer is filled. Next, the logic analyzer watches for trigger condition N to occur again. When it does, the second segment fills. This continues until the final segment of the buffer, segment M, is filled. Storage qualification cannot be used with the segmented buffer. As you can see, it's easy to set up this type of flow control. Just set up and enable the required conditions, and Signal Tap does the rest. However, there is no control over the sequence other than the sequential order of enabled trigger conditions, and no control at all over how a segmented buffer is filled. The state-based flow, discussed later, overcomes these limitations. Continuing our look at the logic analyzer settings, as mentioned earlier, you can select from 3 default settings for placing the trigger position within a non-segmented buffer, or within each segment of a segmented buffer. The center position provides an equal amount of pre- and post-trigger data, while the pre- and post-trigger positions store 12% of the buffer either before or after the trigger occurs. We've already seen how to set up trigger conditions with the trigger conditions columns in the node list, but by default, only one trigger condition is available. You can create up to 10 trigger conditions per Signal Tap instance using the Trigger Conditions option shown here. Changing the setting adds or removes trigger condition columns from the node list. The logic analyzer can interface with other components or external devices. With the Trigger In option, an external signal can be fed into the logic analyzer to act as a trigger condition. This signal can come from an I/O pin set in the pin planner, another instance of the ELA, an internal signal node, or the hard processor system of an SoC device. The trigger in signal behaves like trigger condition 0 in the sequential flow, meaning that it is evaluated first and must occur before any other trigger conditions. You can set the value or transition to look for the input trigger signal in the same way as a basic trigger condition using the pattern option. Enabling the trigger out feature sends an active high or active low signal to another component or device, indicating that this instance of the logic analyzer has triggered. The trigger out signal can be sent to an I/O pin to be placed in the pin planner, the trigger in of another instance of the ELA, or the debugging hardware of the HPS. Sending the trigger out to the HPS is used to break code execution during debugging of the ARM processor, or as a system event that gets inserted into the HPS program trace. The latency delay field at the bottom of the trigger out section indicates how many clock cycles are required before signals coming into the logic analyzer instance generate the trigger out signal. This value, calculated automatically as the logic analyzer is configured, includes all delays through the signal tap instance. This concludes part 2 of the training. If you missed part 1, or you'd like to continue to parts 3 or 4, you can register for and view them for free at the links shown here. To learn about additional resources available to help you with using the Signal Tap Embedded Logic Analyzer, continue to the next slide. For more information about the Signal Tap Embedded Logic Analyzer, be sure to read the Signal Tap chapter in the Intel Quartus Prime Software Debug Tools User Guide. Both the Standard and Pro Edition versions of the guide are linked here. If you'd like hands-on experience with the Logic Analyzer, enroll in the Intel Quartus Prime Software Debug Tools instructor-led training. Besides discussing several other tools that help in verifying a design in hardware, you'll get to work with the SignalTap ELA on an Intel FPGA development kit with direct assistance from an Intel FPGA training engineer. Intel offers many options for learning about our FPGA products and for training on their use. The Intel FPGA YouTube channel contains a number of 5-minute quick videos along with longer, more in-depth training. The Intel FPGA training website is the place to go to learn about our recommended curriculum for every type of user and to register for a class. While there, you can register for over 300 e-learning courses made up of narrated slides presented in an interactive player, some of which include labs and demos. You can also register for one of our full-day instructor-led training classes taught by experienced training engineers, either in person at a local office or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need further assistance, Intel FPGA provides many self-help resources. Check out the landing pages accessed from the main Intel website that are dedicated to specific FPGA technologies like high-speed interfaces and external memory. Finally, you can also view and post questions to the community forum, monitored by skilled Intel FPGA application engineers. One more thing. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Feel free to email fpgatraining@intel.com with any thoughts or comments, positive or negative, you may have on this training course. Thank you for your feedback. My name is Steve, and I want to thank you for taking this online training about the SignalTap Embedded Logic Analyzer.